How's it going, guys? Dylan Codes here, and welcome to day 17 of Advent of Code 2020 in Python. If you find this video helpful, please leave a like down below, leave any questions or comments, and let's get into the solution. So, Conway cubes. As your flight drifts through the sky, the elves at the Information Bureau at the North Pole contact us. They'd like us to give some help debugging a malfunctioning experimental energy source. Cutting edge technology. It's contained of an infinite three-dimensional grid. Oh. And each cube is either active or inactive. Oh, goodness. I think this is going to be similar to the floor problem from the other day. Okay, and it considers its neighbors, which are coordinates differ by 1. During a cycle, all cubes simultaneously change. Okay. And if a cube is active, and 2 or 3 of its neighbors are also active, then the cube stays active. Otherwise, the cube becomes inactive. If a cube is inactive and exactly 3 of its neighbors are active, then the cube becomes active. Okay. So consider the following state. Oh, we have to account for the changes in different z levels based off our 2-dimensional input. Okay, well, let's see what we can do here. So, looks like we're going to be doing some looping today. And I've learned my lesson. I'm not going to store points in the list this time. I'm going to store them in a set, as someone suggested to me in one of my previous videos, because sets are a little faster to access and determine if some points are in. Are already included or not. So let's say with open input.txt, of course input17.txt as a file. Data will equal to file.readLines, and data is equal to line.strip, you know the drill, for line in data. Now we want to get our initial active points. I think it would be a little too much to handle keeping lists of lists that represent the grid. So I think we're just going to store the active points in, like I mentioned, a set. So let's go ahead and say def get initial active points. And so this will just return the initial active points. So active points will be equal to set. And then we will say for I in range length of data. So this is all of our different rows, how many rows we have, and for j in range length of data I. So I is how tall and j is how wide. Data I. Oh, and then we can say if data I j is equal to the active state, then active points dot add, and we'll store the points as a tuple. I, comma, j, comma, and then z is always 0 for the initial set. And I know this is technically kind of like, if you want to think of like an XY grid, this is technically YX, but I don't think it's going to matter. Just kind of inverting the points. What the points actually are don't matter. It's just how many are active or not, and it's all kind of relative. So then we will return active points. Okay. Now, I'm not going to write our solution in a function today because I recall previously you can't just like, if you have like a global list, you can't just like set a new list with inside the function to the global list. Or something like that. There was something weird. So I'm just going to do them as loops on the outside. So we'll say part1 and active points is going to be equal to get initial active points. And then we're going to update this active points list. And then it did say we are running how many? Okay, 6 cycles. Whoops, got to see behind the scenes there. Okay, so we're going to say for R, or for blank, in range 6, so run it 6 times. Then we're going to say, so we have our current active points. And then all the points are going to update simultaneously based off our current state. So we need to store the new set of active points in a list, and then at the very end of the loop iteration, we'll update our active points. So new active points will also be equal to a set, and then we're going to loop through all the possible x values, all the possible y values, and all the possible z values. So for I, or let's say for x in range. Now, how many wide is this? So this is initially 8 wide, and we're going to go through 6. So with each iteration, I think we have the potential to add 1 level, because right now this is 6 wide, or this is 8 wide, but technically we also need to consider the point on the right and the point on the left, which could be updated. So then that means the final width will be close to like 16 if we multiply 8 by 2. But if we have those loops going through a 16 by 16 over and over and over again, that's going to be a lot of iterations. So I think we can dynamically determine how many points will loop through each time. So if we say for R in range 6, so this is which cycle number we are. And we can say, because on the first round, our x values only need to be, like, I don't know if you want to consider this, I guess technically in terms of our indexing, this is 0, 0, but technically we only need to consider, like, if we were to consider 0 to be the middle, we'd only need to consider negative 9 to positive 9 or something like that. Well, let's just do negative 10 minus R, because this is 8 wide. This is 8 wide here, and so then we would get, if we add 1 here and 1 here, that's 10 wide. So we'll just go negative 10 to 10. So negative 10 minus R, and then as the rounds increase, we'll check farther and farther out. And then R plus 10. And then for Y in range, negative 10, same logic here, negative 10 minus R to R plus 10. And then for Z in range, now Z is different. So Z, we're starting at 0. And then we need to check, so we have X, Y, and then that's in our initial state is in Z0. So we also need to check Z negative 1 and Z positive 1. So that adds 2 to, so we have one Z plane, then we have an extra one and an extra one. So we have the round number plus 2. So we'll do negative 2 minus R and then R plus 2. I think that should dynamically cover our Z's. So now for every point, we need to check its neighboring points. So we'll say check X, Y, and Z point, and then for the current X, Y, Z, check the neighbors. So the neighbors can be either can be up to a maximum of 1 away in any direction of X, Y, or Z. So I think I'm going to pull out some physics, some I hat, J hat, K hat for like vectors and stuff. We're going to say for I in range, and it could be negative 1, 0, or 1. So we'll say range negative 1 to 2. 2 won't be included. Only positive 1 will be. And then so that'll represent the X direction. for j in range -1 to 2, and for k hat in range -1 to 2. Then we'll say, now this will get 9 points. The 9 this will get all, or I don't know if it's actually 9, but this will get all the points surrounding our current point for XYZ in all directions. But this also includes our XYZ, and that would, and relative to these points, our XYZ would be found at I0, J0, K0. So we need to say if not I is equal to 0, and k is equal to 0, and j is equal to 0. So if we're not looking at our actual point, then we'll say if tuple here, x plus I, comma j, or y plus j, comma z plus k in active points. So so what this checks is, so for our current point that we're checking, then this is not the ijk is not the location of the neighboring point, but it represents the distance away we are from a certain neighboring point. So say for example I is equal to 1, then and we do x plus I, then we're looking at a point that is 1 x value away. So it's like, so if we add our current point to a distance away, then we get a neighbor. And if this neighbor made up of x, y, and z is in our currently active points, then we will say that active count, which is initially equal to 0, then active count, active count plus equals to 1. And then so once we check all the neighbors, then we can say apply rules. So if x comma y comma z, so what are the rules again? If it is active, if the current state is active and 2 or 3 of its neighbors are also active, then the cube remains active. Okay, so if XYZ in active points and count is equal to 2 or count is equal to 3. And if we're going to write it like this, it's very important that we put this part in parentheses, because it would evaluate XYZ in active points and count equals 2 or count equals 3. But we want it to be this and that. So precedence matters here. And then that should be active count. What? Why didn't that not work? Then new active points dot add x comma y as a tuple, and then we'll say if x comma y comma z in or not in active points. So if XYZ is not currently active, but 3 of its neighbors are active, then the cube will become active in the next iteration. So if not in active points and active count is equal to 3 exactly, then it will go from the inactive state to the active state. So dot add as a tuple x comma y comma z. And then at the very end, if we've checked XY, so if we've checked every point and all of that point's neighbors, then we've added all the appropriate points to the new active points, and then we'll just say current active, we'll just say active points will now be set to new active points. So our new set of points will be used as the current set for the next round. And then at the very end, once we're done running that loop, print length of active points. So active points, after this loop is done, then this will be a set of all the active points after 6 rounds. So if we go ahead and run that, of course we have an error. And what line is this on? Line 10. Should be added as a tuple. And if we run now to 11. Fingers crossed, as always. All right, so there is part 1. Now I wonder how they're going to spice it up for part 2. For some reason, our simulated results don't match the experimental energy source. Apparently, the pocket dimension actually has 4 spatial dimensions, not 3. Oh, that's scary. Yeah, they can say it's a hypercube. So we also have to consider dimension W, but each cube still considers its neighbors by the same rule. The initial state is still the same, and it still considers the number of active neighbors. So we still have a 2-dimensional slice in the initial state. So our input represents here a 3 by 3 by 1 by 1 region of the hyper or 4 space W coordinate. And I'm guessing the same rules still apply. Okay, let's do this thing. So here we'll say part 2, and I think we're going to have to modify this function ever so slightly. So we're going to say active points is equal to get initial active points, but we need to determine if we want 3 or 4 space. So we're going to say 4 dimensions. So 4 dimensions, and it's just going to affect here. So if not 4 dimensions, so 4 dimensions is going to be a Boolean. If not 4 dimensions, so this is for part 1, then add ij0. Else add active points.add ij0 0. Okay, and we will say 4 dimensions is false. Now let's just go ahead and make sure we still get the right answer after that modification. Okay, 4 dimensions true. And okay, part 1 still gives us the same answer, so we didn't break anything. And then we're going to say, I'm going to copy our code from part 1 because it should be similar. I think what we can do is I think we can just add another level where we check for W. And W also starts in 0. This is really hard to visualize because it's 4D. Hypercubes are actually really cool. There's also like this virtual reality game. I've not played it, but I've seen it out there called 4D Toys. And it's really interesting because like we can only visualize in 3 dimensions, but in 4D Toys, you can play with 4D objects in a 4D space, and sometimes you just move it and it disappears because it's gone into a different cross-section of the 4th dimension. It's like trying to put something in a simple hole. If it's like impossible. Check it out, YouTube. Sorry, I apologize for getting off topic. Okay, so now for every x, y, z, w, scoot this over a little bit. for every XYZW, and scoot this over too, for the current XYZW, check the neighbors. So then we'll also say for, well, normally only go IJK, so I'm going to say for, let's say for P, in range -1 to 2. So this really just follows the same logic. We're just checking a fourth level. And I think in this case, it's really going to matter that we have done this dynamic size checking here, because I mean, if we just did like 15 to 15 or 16 to 16 each time for 4 loops, that'd probably take like, that'd take a long time, I'm guessing. So so for P in range, and then if P is equal to 0, okay, so if not, also P is equal to 0, and then we'll say W plus P. If W plus P is an active point, it's an active count +1. And then if XYZW, then add XYZW and XYZW because we're playing by the same rules. And then print len of active points. And if we go ahead and run that, 211, we're going slower on this one. Okay, I'm gonna go ahead and break that, and we are going to print the len of active points after each go around. And if we run that again, yes, you can see we go nice and slow here. All right, and 1952 appears to potentially be our answer. And there we go. So there you have the solution for day 17, Advent of Code, 3-space and 4-space with some hypercubes. Now that solution was actually kind of slow, and it probably has to do with the fact that we're looping so many times and we've added this 4th level of looping. But what you're going to do, this is a working solution, and for the input we were given, it works just great. So if you have any questions, leave them down in the comments. Subscribe for day 18, which you will see tomorrow, and have a good one.